Let's go. First stream of the day, day 17th. Dear YouTube, it's been a journey. Let me share the latest link. Hope you guys are doing well. It's a beautiful Sunday. Perfect time to spend streaming 10 hours today. We're gonna wrap up the work we started yesterday. Basically getting the eval to work on both GPUs using FSDP. That's the plan for this stream. Let me wait for people to join. Latest stream, getting eval to run on 2 GPUs using FSDP. Will be fun. Don't expect it to be too hard. I'm gonna regret this sentence immediately as soon as I said it. Okay, that's gonna be the first part, and then in the second part of this first stream, I'll be piling up some tasks to our GitHub project dashboard. Okay, I hope you guys are all doing well today. Awesome. Let's get started. So we stopped at fairseq. We managed to debug the weights and biases issue last night. So let me quickly recap what we've done. We have this intermediate translate and eval function, which I've disabled for some weird reason. Let me see why. Okay, because I'm still playing with FSDP here. So the function, what it does is it basically converts the model, it puts the model into the eval mode, then it goes over all of the language directions we basically support by doing this for loop here. And then we grab Flores source sentences and we translate them into that particular target language. And so we collect all of those samples and we log them as a table to weights and biases, so we can track how the progress of the machine translation model is progressing, how the progress is progressing as we're training this, just to have a qualitative understanding of how it's making progress. And finally, we also evaluate on Secra Blue metric. So we use the CHRF++ is the name of the metric, and we log that one as well as a scalar to just track progress on the dev test of Flores as well. That's what the function does. Now let's get it working for the multi-GPU setup. So I'm thinking, what's the best way of picking up the rank here? Let me see how they've done it elsewhere in the code. If we manage to do that, then we can just split the work. Different chunks of the work will be done on different GPUs. And at the end, I'm gonna merge and synchronize the GPUs. So let's see. Validate and save. So far, so good. We are here in the train. This is the main function. Let me just quickly see where train is called. Train is called here. And there is no difference at this point here. There is no difference between 2 different GPUs. So let me see, when do they start separating them? Not here. We don't care about this one. This is for gradient accumulation. We don't use TPU. Progress bar. So there is one moment where they separate them, and that's here. If it's master, then only that GPU should be logging. As you can see here, only if it's master do we have weights and biases set up. Okay, and then let me see what we do here. Is there any separation between different GPUs? I don't see it yet. So we grab the samples, we call the train step, and then we do validate and save here. So let's maybe enter validate and save. Let's see whether there is any difference between different GPUs. I guess the difference comes from the iterator, which in the background gets the rank and then splits the work. I think that's going to be the main difference. So here, nothing special. Let's just go to validate method. Do we see any difference? I don't yet. Get the iterator. Again, we pass it in here. We have this isMaster, so that only a single GPU is logging to weights and biases. And then we start doing the training steps here. So we can enter easily in there. Let's go there. Set the model to eval. Oh wait, why didn't I do this? This was stupid. I should have put a no grad context. So that's one thing I forgot. Let's go back here. So once we start inferencing, let me see where they do it. They add the no grad somewhere here. Just a second. So validation step. So just before we convert to eval, and then sample, prepare the sample. Okay, so they called that one before the validation step. That's the important bit. Okay, we'll get back to validation step. Let's go back to train. Let's go back to our intermediate one. So where we want to set it to no grad is likely here, or just at the beginning of the function. Both will work, I assume. We are not tracking anything in here. So should we just put the for sample, this whole loop? This whole loop should likely be under with torch no grad. Just like that. And that's it. Save that, go back to train. Let's go. Prepare the sample. If the frequency, so this is for mixture of experts model. Otherwise we skip all of that and we just do the train validation step here. And then if there is a runtime error, we do some stuff like we log it, and if this is not raised, then we log, go through the parameters, free up some memory, and empty the cache, and try again validation step. Just a recovery routine. Otherwise, let's see. Otherwise, so here is where they gather the results, right? So they separately run up there, and then they gather the results here. If the data parallel world size is bigger than 1, then we aggregate. And then if TPU some additional logic, reduce and log stats. So these two are going to be potentially interesting. So let me just disable all of the breakpoints except for these two. Okay, let's enter the aggregate method. All gather, let's sync. Let's just enter here. Let's just play a bit with this code. So I'm gonna run this and see what exactly happens in these functions in the trainer. Aggregate the logging outputs, train step, valid step. This is what we care about. Also likely about train step, well, not this one, but this one. Might be cool to just step into quickly and see whether there is any difference. Aha, so we are already here, but we did not enter. We entered here through the train step. If sync stats, let's understand what all of these exactly do. It's going to be good learning. And a very much necessary learning if we're about to implement this at all. So we had prepare, and then at one point, where is the train step here? No, this is the train step, sorry. So we prepare the sample, and then we enter somewhere here. What's this? Huh. Not sure. If cell CUDA number of updates is 0, then we empty the cache. Exceptions. Okay, aggregate the results, and the logging output comes out of where? Logging output. Okay, here is the train step. Here is the train step of the actual task. This is in the train step of the trainer, and this is the train step of the task. And this is also the train step. Okay, let's just keep on iterating. Let me see what this does. Fast stat sync sum. What happens here? So we have some logging output. We have the loss, the NLL loss, the number of token sentences and sample size. Extra status sum. What is this? Okay, some tuple. I don't know what it is. And then ignore, set to false. Let's enter here. Sync logging outputs across workers. Fast stat sync sum is faster than all gather list sync, but is only suitable when logging outputs are scalars and can be summed. Note that logging outputs cannot contain any nested lists or directories, dictionaries. Okay, so that means we will not be able to use this because we have to aggregate the actual sampled sentences. Let's see where we hit this other function that's suitable for those types of workloads. But quickly, let's see what this one does. So we go through here and we just add extra stats, whatever those are. And then we pick up the keys. And then we go through the keys. And if we're not ignoring, then we just sum up. So for key in the log, so for log in logging outputs, which is only going to be a single one, we grab the values. 28,000. Okay, that's the loss. And then we see logging outputs with the loss and then value. Okay, so we just populate all of that, and then we go here. Distributed utils all reduce a dictionary. So we have data with a ton of scalars and a couple of scalars but wrapped in a tensor. Device set to CUDA and data parallel group NCCL is what we are using in the background. So let's see what this one does quickly. So this one is still in fairseq, distributed utils all reduce dictionary. We grab the keys. We'll reduce a dictionary of values across workers. We separately reduce items that are already on the device and items on CPU for better performance. Okay, so that means we're going to split device and CPU data. So we go through the data. If it's a tensor, if it's not a tensor, then we convert it into a tensor, D-type double, but this is going to be on the CPU. And then next up, okay, most of them are going to hit there. Some of them are gonna go here, and if the T device type different than device type here, in that case we go here. Otherwise, good morning, David, was it right? Torque float 64. So we move this, which is on CUDA. Okay, we just store it here. They here convert to double. Okay, they convert all of them to double. That's it, and then we're gonna have the rest of them are gonna be CPU data. Okay, I think that's almost it. That's it. Let's go here. All reduce a dictionary. Okay, so now we first all reduce the CPU data. I guess we'll have to advance this one. Okay, now they're both here. Let's see how this is gonna work. So all of them are float 64. And all of that is just CPU data. Okay, let's go. So what we do, we go through data values. We flatten them out, we concat them, and we push them to the device, which is gonna be CUDA. Okay, so these are all the CPU values, and we end up with a buffer, which is, as you can see here, now a GPU tensor, and then we call with the buffer, and with the group, we call all reduce. All reduce is still in fairseq. Do we use sum or what? Sum by default. So we go and call this all reduce, this particular tensor, using a sum, using this group. And I think this is going to be a blocking call. Let's see. I'm going to enter for now. Check that single tensor. If rank not in group. See what this one does. I'm just curious. Return whether group is a non-group member. It's not. So if tensor is complex, which is not. Okay, and then we call NCCL. So this is NCCL primitive object or whatnot in C. And we call all reduce on the tensor with this. And now when I click F11, this is gonna kick the second process to advance, I guess. How did this even work without? Aha, so now we have to wait. And so now we kick off this second one. Let me see what's gonna happen. All reduce. Interesting. How come this one, the second one, did not move? So we clone the buffer and split it 14 data values. We see how many elements and we split it. And then we, I guess, reconstruct it. Split buffer, zip with data values. T and original, view as original, reduce data. Let's see what we get here. Let's print the value. It's still none because I assume we have to kick off the second process. Let's quickly go here. Let's go here. Okay. Now we can see it. Here it is. So we went through the split buffer and data here. What's the difference? 23,556. Okay, some magic happened there. I'm not completely sure of how the numbers were moving. Let me try and understand this. What happened? So buffer should be modified in place, right? Yeah, we're gonna put a breakpoint here so next time we can log the data exactly. Reduce data. Let's go back. Aha, so we now do the same with device data. Let's see how that's gonna work. I'm gonna advance the second one as well. I'm gonna advance the second process. Let's enter here. So this process has data, values, logging outputs loss. Let's just log this somewhere here so I can quickly put it on the side and understand what exactly happens. So I'm gonna just grab this, maybe try and do data but like as a string. Okay, that's easier. I'm gonna put it into my Notion quickly, and then what we do is we flatten it and we concatenate it, so we get a buffer that has those two data points. Okay, and then we call the all reduce. And did anything change with the buffer? I doubt it, because okay, nothing. I cannot print the buffer, that's the thing. So I cannot print it until we go with the second one. So let's grab the second process. Let's see what its data says. So here is its data. So a bit different value, 2, 1. Okay, let's grab this one. Okay, let's step over. So we end up with 28, 8184, 28116. Okay, let's all reduce. And now let's see what we have in the buffer. So we now have 57557, which is the sum of these two, and we have the second one. Okay, it's just okay, as the function says, they're just doing summary. They're summing and reducing across the two. So if we do calculator, previously we had values like, just clear this. How does one clear this? Okay, whatever. So grab 29435. That's the first value of the first dictionary plus 28121 and 57556. So that should be the first value of this buffer. 57556. 57557. A bit difference there, because I ignored some of the floating. I ignored the number after the floating point. So that's actually a good result. Let's continue. We now split it. We go through the data values. We see how many elements and we split the buffer. Okay, and then view as the original. And that's it. Nice. And now we grab the keys and reduce data and we just retrieve that back. That's it. And then go to the keys. Data keys. Where did we get this one? Okay, that's just from before when we entered, and we now somehow have to combine device data and CPU data, and they are just called internally here from the outer scope. And so when we pass the key, we go to the keys, and then we grab the key is in CPU, we return that piece of data, otherwise we return the other one. Okay, so we just order dictionary. Makes sense. Let's go back. and that's the fast stat sync sum. That's what that one does. Looking good. I think this is the first time I've stepped through function like this here. Are you looking into how distributed learning is handled? We are looking into understanding a bit better how it's done here in the code base, so that we can implement the same thing for our use case, which is eval, and trying to sync the values between two GPUs. Sample text from the floor is 200 basically. Okay, extra stats to sum, and that's it. We grab the data after the all reduce, and we now, what did we do with the data after we reduced it? If it's not none, okay, we just picked it here. Let's go up. So was that where did we run that? Was it this function or yes? Okay. So we are now back. We have our data back, and now just cumulative time. So, okay, we can now run F5. We can remove this breakpoint, hit F5. Okay. And now we're here again. Let's understand what this sync stats does. Okay. Train step is here. If sync stats, let's enter into this one to see what this one does. So if it's equal to, if this is equal to 1, then we return false. So return true if it's using multiple GPUs and DDP, or multiple GPUs with BMUF, and it's a BMUF sync with warm-up iterations complete before. I'm not sure what BMUF is. Let me just quickly Google that. What is BMUF? Distributed computing, distributed. What's BMUF? Communication efficient distributed optimization framework proposed by researchers from the speech group there. I've never heard of BMUF. Maybe I've seen that can be found in fairseq implementation. Okay, whatever. So because we are not equal to 1, we just return true. So this is going to return true for us. Sync stats. And then again, we enter here. We enter this. And then we ask, logging outputs can be summed for this criterion. We'll probably have to call this one, by the way, guys. This is going to be the result that this will be the function that we'll be running, likely. So here, the same thing, we're going to just skip this function. We've done it before. Hit F5. Just hit F5. Let me just advance here. And that's it. Let's wait until we hit the breakpoints we've set in the validate function. That's what I'm waiting for. Okay. What's going on? Okay, here we are. We're now in the validate step. We've set the model to eval mode. We've done some asserts, and now we're running this. Let me quickly see whether there is anything interesting in here. Enter here. Okay, not really. We just run this on separate GPUs. And once we're done there, once we finish that, then we have the logging output. And then we gather the outputs. Let's see again what this one is going to do. Will we again hit the same? Likely we're always going to hit this branch here. We're never going to hit this particular branch, I think, because we get the criterion. And then let's see what happens when we step into this label smoothed cross entropy criterion. Let's step into this. Okay, so for this particular criterion, it's set to true. Whether the logging outputs returned by forward can be summed across workers prior to calling reduce metrics. Setting this to true will improves distributed training speed. It can, and so we enter here. Let's exit. Okay. Let's advance the second process. Okay, my VS Code is a bit slower for some reason now. Okay, I think this is the wrong process, this one. Are they on the same location? 1, 3, 1, 8, and this one is on a different place. Okay, let's go. Let's advance this one. Okay, we need to advance this one until we get to the logging outputs. Hit run. Remove the breakpoint from here. Exit. And here we are. And now we call reduce and log stats. Let's see what this one does. If grad norm is not none, which it is, so we skip over that whole part. Otherwise we'd be logging some stuff there. And then here we create a new context manager aggregator. We enter here. If logging output is not none, which it's not, we call reduce metrics. Okay, why do we do reduce metrics here and we didn't do it before for train as well? So what we have here is, let's see, loss, NLL loss, number of tokens, number of sentences, and sample size. And then language indices. Let's enter this method. So we grab the criterion and then reduce metrics with the criterion, calling the superclass of this task, which means base task probably, fairseq task. And then base function aggregate logging outputs, which does something. Okay, let's put a breakpoint here. And then we try and get the aggregate logging outputs function. grab the number of tokens. And then we log them. And then we sum. And we log them. And then we call criterion class reduce metrics. So we call the class level method reduce metrics with the logging outputs, which have not been modified. We just extracted some information from them. Okay. Let's enter. See how the label smoothed cross entropy reduce metric class method works. We grab the loss and we sum it up. Same here, same here, same here. And then we just log. And then utils item total if it's bigger than 0, otherwise we exit. Okay, so it's mostly about logging there. Nothing happens really that's of relevance to us. Get smoothed values. And then we delete some stuff. And then we exit here. Okay, so this was not really super interesting. Reduce, this is not, there is no synchronization happening in this piece of the code. The whole logic happened actually here. Aggregate logging outputs is where we have to all reduce across the GPUs. And that happens after the valid step happens just above here. Okay. Let's exit. Let's exit here. Will we have anything interesting there? Nope. We can just exit the whole validate step. I'm going to remove this breakpoint. Exit. Exit the valid step. Okay, let's just put breakpoint here until we wrap up with the validation steps. Okay, we can now exit here. And then we repeat the same process here, I guess. Okay, so I think I have everything I need. Let's quickly go once more to the train logic. I want to exit this whole validate and save function. I want to enter the train logic. I have to remove this breakpoint again. Exit here. Okay, we're here. Now comes the train step again. Quickly, let's step into it. Let's see where the whole smartness happens here. I'm going to put a breakpoint here, hit F5, run to there. Prepare the sample. With maybe no sync. Let's see what this one does. If this is bigger than 1 and model has no sync and length of I is smaller than this and is not FSDP, okay. Otherwise this is going to be just exit dummy context manager. So nothing smart happens there. So train step, I don't think in this train step there is no communication between the GPUs. They just do a forward followed by a backward and then they return back. Okay, so this happens on a single GPU independently. And then we call GC collect. What does this one do exactly? Garbage collection, or what is this? What is GC? It's from standard library. Let me just quickly see what it does exactly. We just clean up some of the hanging references or whatnot, but why would they call it there? What's so special about PC collect Python garbage collector? Why do you explicitly call garbage collector there? PC collect, run a full collection. Okay. Interesting. That they are explicitly calling it right there. Every now and then. And then we append the logging outputs from that GPU. So we'll do this for both processes. And afterwards, now we're doing what? Let me see. Okay, we stepped over this. Sample size, if it's a tensor. Why are we skipping all of this? What's going on? Why are we invalidate? Okay, I'm just getting triggered by different processes. So this is now, again, this is the second process, second GPU. We're gonna run the same code. Let's just step over this. Remove the breakpoint there, hit F5, get here, GC collect again. Okay, we are here. If sync stats, which is going to be true because we're running on 2 GPUs, get the cumulative time, and then aggregate. And that's all the fun there is. Afterwards, there is the optimizer all reduced. Anything else that's interesting here? Multiply gradients. Again, optimizer stuff. Gradient norm. If not CPU, check for grad norms, check it's not infinite. Again, optimizer stuff. If there's some errors. Otherwise, we get here. I think we skip this part as well. We can put a breakpoint just in case. Yeah, let's put a breakpoint there, and then we can step through the rest of the training. But that's pretty much it. The whole magic of syncing the information happens basically here between the 2 GPUs. So again, we've been in this function multiple times, and we always hit this one. We apparently never hit this one. Let's analyze what happens in this one. So we here do all gather list sync logging outputs across workers suitable when logging outputs are complex types. So this is what we are going to be using. List of dictionaries of strings, if any. Interesting. So we grab the logging outputs, all gather list. Here's the group. The max size is either this number, or if we have all gather list size, it's the same number. And then we have logging outputs, and we add extra stats to sum if there are any. Convert that to list, call this, zip it, list it, get the results. Okay. And then we return back the, okay, we're gonna be using this one, but we always enter this second one now. Exit. Let's continue, hit F5. Hit F5, and we're down there. So as I said, we skip this part. Set the number of updates to the trainer by +1. And then log GPU mem stats, nothing special there. Reduce and log stats, we've seen what this one does before. Just logs to the meters. log scalar, same as this, just happens internally there. And then we go here and that's it. So once we exit again, train step. After that we call this, okay. So I think we have everything we need. Find task, train step. After it, find the logic here. And we care about this trainer. Aggregate logging outputs. Actually call directly this. We're directly going to call this one. Let's stop this. Remove all of the breakpoints, disable them, stop the run. Go to the train script. Go to our function. Uncomment it. We're going to be testing this one now. Go to the implementation. Okay. So after this is done, we'll somehow have to integrate this logic. I'm not sure whether this one is going to do the job for us, by the way, because it's for all reducing. It's not for what I'm actually trying to accomplish. We have a partial set of data on one GPU and a partial set of data on the other one. We have to share those two between the GPUs. That's the idea there. So let's see. How do we get the rank? Is there any mention of the rank here? Rank. Get the global rank. That might be it. Get the global rank or local rank. Let's see. Get the rank. Get the global world size. Let's see what we have on disposal here among these functions. Broadcast. All gather lists. We've seen all of these. Broadcast answer, broadcast object. Well, we'll definitely find something that's of use for us in the distributed module utils. Something here will work. Broadcast. Get model parallel world size. Get model parallel rank. Let's call all these and see what we get. Model parallel, this should always return 0 because we don't have any model parallelism. Global rank. Get rank. Okay. Is master. Calls distributed rank and asks whether it's set to 0. Okay. let's see where these ones are used. So I'm just thinking also into the future. If we're running on multiple nodes, what happens then? How do we want to distribute this data? I basically think we need a global rank here. I'm fairly sure we just need this one. But I want to call all of them just to see how they work. Where is this one called? Just curious. Okay, I'll run the place. Generate, evaluate, pre-train, cross entropy, initialize, layers, transformer, test. Let me put my train function here, my train script here, and let's just aggregate all of these functions somewhere here so we can play with them. And I'm going to put my expectations of what should be logged before we go, just to double check my understanding. Our setup is fairly easy, so 2 GPUs, a lot of these will give the same results in this special case. But that's it. Get the global group, get the world size. What's the difference between the world size and the global world size? We're gonna step into all of these. Okay, that's it. 8 of those. Model data, global and world. Excuse me. Are any of these called already here? Nope. Okay, this one is. Get the global rank. So distributed utils, that's how this is called. Okay. Go back to train. Let's see for the other ones. So this one requires a group to be passed in. So get the world size for the group. Okay. We don't care about that one really. And also get rank also. So that one gives you the size for the group. This one is truly global. So that's the difference. So what we'll need is just a global rank. And we'll also need the global world size, I think. Data parallel, this one probably requires you to, okay, this one just fetches the data parallel group. Same here and same for the other ones, I guess. Yes. So let's just play with these and see what they give us. Okay. Okay. So what I expect is print all of the above. So what I expect is this one, model parallel, I'm expecting this one to be 1, and thus this will be 0. And I'm expecting this to be 2, and then this will be 0 and 1 depending on the GPU. This is obviously going to be 2, and again 0 and 1 depending on the GPU. But we don't have any model parallelism, so that's should always be same rank, and the size is 1 or 0. I'm not sure how they're counting that, but this we don't use this. Well, the thing is FSDP in the background kind of does the parameter sharding, but let's see. Okay. So once we have this, we can split the work. And once we split the work, at the end, we'll want to aggregate the data, share it across the GPUs. We're going to see how we do that. For now, let's just disable all the breakpoints and just put, whoops, disable all and put a breakpoint here. And now run the training. Let's see. Almost there. I can hear the GPU humming. Okay. Let's see what we get here. This one is also 2. And this is 0. This should be 2. This is going to be 0 then, I guess. This should be 2, and this should be 0. Okay. Because world size and rank global ones are now the same as this one because we only have a single node. But in general, if we have multiple nodes, then this would be different. If we had 2 nodes with the 8 GPUs, this would be 16. This would be 0 through 15. Data parallel, well, depending how we distribute it, but if we had like model parallelism across 8 GPUs and then data parallelism across the 2 nodes, then this would be size 2 again and 0, 1. It all depends how you set up your system. But this kind of confused me. Model parallel is, interesting. Let me switch to the second thread, to the one above, and let me enter quickly. So get model parallel group. So model parallel group does not exist. And then we go and grab the world size. For the group none. So this is, yeah, this is basically just returning the group size for default group. That's why we get 2, because it does not exist. So we just grab the data parallel group, I guess, and then default size. That's it. That's why we get that number. And same here. Get the model parallel group. That one gives us none, and then get the rank for the group, and we get it for the default group. Okay, makes sense. Okay guys, stopping the run for now. That was all I wanted to do there. So we can delete all of these. We don't need this. We don't even need this. We just need this. And then what we need to do is, now that we have the world size and the rank, we should distribute this work. So all of them will have the same settings, so this remains the same. All of them should go to model eval, get the model, and then all of this is so far good. So here we want to split this work. And then at the end, scatter the results and log to weights and biases only on the master, only on the main one. Is master basically tells us whether a distributed rank is 0. What does that even mean? Do we even pass anything to master? Yes, we do. So this is set somewhere in the code, probably initially. Let's see where. Okay, somewhere here is where we set it in the beginning. Let's just put a couple of breakpoints here, 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 or here. This is just assert. Here. This is pipeline. We don't need to do this. Pipeline. Pipeline. We can ignore all of this. Again, pipeline and pipeline. We don't care about those. Those are in the pipeline. In first Slurm, we also don't care about this one in all reality, because we are not on Slurm. And that means we're gonna hit this one. This is the one we'll hit, which I'm surprised because we don't really have rank set, at least not manually. So let's see what happens when we run train. When we run train, do we hit that one initially? Let's see. Moment of truth. Currently not. So then how do we differentiate between the two processes on two different GPUs? Let's see what the config, let's see whether that value is still changed somehow through some other means that I'm unaware of. Waiting to hit this line. And then I'm gonna quickly call the isMaster, this function. I can hear the GPU humming. Let's hit this line. Okay, debug console. isMaster, this one is true. Let's progress and let's go to the second one. Let me just see, config distributed training. World size, number, distributed rank is 0 for this one. Distributed port device ID. Okay, just a ton of different settings, but those are the main ones. Let me now change the process. Let's go to this one. And if we call the same function here, we get false, because if we print this for him, for that second process, distributor rank is set to 1. Okay, so somehow, somewhere, somebody sets that distributed rank. I don't know how. So let's see, distributed rank is set somewhere. Multi-corpus, maybe here. This one just checks, but who sets it? We never hit this apparently. Okay, maybe we've hit some of these in first learn minute. Let's see, maybe we hit some of these. But it's certainly not pipeline. There is no way it's going to be pipeline. Aha! I've missed these ones. I've completely missed this one. Completely missed this. Okay. So now I've set breakpoints to all of these. Let me just understand where this happens. It shouldn't be in the slur minute, that's for sure. It should be in this one that I just newly found. Okay, let me stop this. Let's rerun the train. Hit run. This should be fairly quick now. In the very beginning is when this happens. This distributed setup. Okay, here we are. So, okay, so we set it to none initially. Call main, let's hit F5. Assign automatically. Okay, and now in distributed main. Got it. So we have I is set here. And so I sets it up. This is going to be 0 plus, okay, because this distributed main is called from here. Let's go to train, to the bottom of it. CLI main ends up calling the main here. This one ends up calling distributed main, which is here, and grabs the device count and the world size to set the number of processes. So that's how we get it, exactly here. And then again here, for some reason we set it multiple times. Let me just grab the second one. And we end up here. Okay, just a dummy reduce to communicate all of them distributed in it. We do a dummy all reduce across all of the GPUs after initializing the backend with NCCL, TCP, world size, and rank. And now we get the distributed get rank, which calls what? Gets the default group and returns the rank. Okay, that's it. Now I think this particular function is called also somewhere among the utils we were using. So if we go back to train, if we go to intermediate, if we go here, somewhere in this file I remember we were using this, get the global rank. So get global rank calls this one, which is called here to initialize it as well. Okay, so just remove all of these breakpoints, disable all of them, and so that means we can just run here global rank. It gives us the same rank. Okay, makes sense. Now onto the real task. So these are the target lengths. Let me call them like that. And then depending on your rank, you're going to pick up exactly. So we start from the rank and we just iterate like this. What happens if we, okay, we have to catch the edge case here. What happens if number of ranks is bigger than the number of target languages? If for some reason we are training like a bilingual model on 8 GPUs, this would fail with index out of range exception. So in that case, we have to just check for that case. So we can just do something like if you're smaller than then do something. Otherwise, I guess this. Let me see what they've done here. What Copilot has proposed here. I propose to just duplicate this. No, we don't want to duplicate the work. We just want to this is what we want to do actually, right? So we have our target languages, and if this happens to be a rank that's bigger than target length, in that case, bigger or even equal. Because if this is 7 and this has 7, we don't want to index into it because it's going to be again exception. Otherwise, just split the target lengths and then finally go through them, do your workload, do your sampling. So grab the iterator for that language, set the codes, build a generator, progress, wrap into Node-Grad, start sampling, log the progress, get the hypothesis. We'll remove this a bit later, and then at the very end, revert back to the original, not state, but state, and then scatter the results. So let's see what we need to call here. Once the results are scattered, in all reality, we don't even need, we just need a single GPU like with rank 0. to collect the results. To collect the results and to log them to weights and biases. That's all we need. We need to accumulate all data on a single GPU. We don't need every GPU to have every piece of data. I'm not sure whether that makes things a bit more efficient. If anybody knows, type it down in the live chat. But if you know, you're probably not watching the stream. You're probably building the next GPT-5. I'm joking. Okay. Now, how do we gonna do this? Okay, let's assume that we have the necessary data. In that case, we want to go through the languages and sort them. And then only if you're a master, then you do this. And then we put step 1 actually needs to be in here. So what we do is we go through the generations. We grab the translated text and the target text. We compute the CHRF++ metric. And we log it. In step 2, we grab 20 random samples per each of the languages. So for each language, we grab a random sample and we collect those sentences and we compute the score and we log that as well to the table above, and then we save the table. And then we also stop the eval wall. And we log it. I'm just looking because currently all of them kick it off here. All of them are kicking it off here. Here. So maybe we can stop just before somewhere here. And then this one will collect it and log it. Okay, this looks good. The last step we have to do is this. How do we scatter results? And then we can probably place this inside here as well. Do they do any synchronization at the end? Let me think. I don't think they do. Okay. They're gonna synchronize naturally on some of the next blocking calls. That's fine. They'll just wait a bit more for this particular master process to wrap up this. So let's see how we scatter stuff. So let's go to the utils, I guess. No. Where is this function defined? is defined here in the trainer. It's defined in the trainer. And this is in particular for logging the outputs of the neural network. So we'll not necessarily be using this. We'll be using just something from this package instead of this pre-prepared this function that's been kind of in the trainer for special purpose, and that's to sync the logging outputs across the workers. What we really need is some different function, some different primitive. Let me see what of these actually makes the most sense. I'm not sure how it should be called. Okay, these are just infer methods, pipeline. We don't care about any of those. None of that matters. So it's not going to be all reduced because we don't want to sum. For all reduce, everybody has to have the same parameter, and then we somehow combine them either through max or sum or whatnot. So it's not all reduce. Broadcast, it's not all to all again. All gather list. Reduce dictionary, we've seen this one being used. Broadcast tensors, broadcast object slow. Split tensors, split tensor. Is there any scatter? There is no. Let me see these operations. So if we want to have, I'm not sure what's the name of this operation. So what is the difference between scatter, all gather, all reduce, broadcast? We don't need the NCCL part. We just see in general. Collective operations. Okay. So in broadcast, one sends the data to everybody. Reduce, collect data or partial results from different processing units and to combine them into a global result by a chosen operator. Or reduce. Gather. I think we're gonna do gather. Store the data from all processing units on a single processing unit. That's what we want to do. We want to gather. Given P processing units, message MI on processing unit PI. For a fixed processing unit PJ, we want to store the messages on PJ. Can be thought of as a reduce operation that uses the concatenation. This works due to the fact that the concatenation is associative. Okay, we want to do gather, not scatter. Okay, let's see what we have among these functions here. What do we have that does gathering? We have the all gather. We have the all gather list. I mean, we can use all gather. I'm just going to disregard. It's probably going to be equally expensive. Okay, let's see. So it's going to be all gather list and all gather. That's all we have. Right? all getter list and all getter. Those are the two we have. So let's see. Perform an all getter operation. Get the world size, get the rank, tensor, or tensor list. We call the all getter of the tensor list. And okay, so tensor list is created how? We go through the if I equals rank. So we go through the world size. This might be problematic because this one is again fetching some group. Can we just do it globally? I guess all getter is not that efficient when we go past the single node. So let's assume for now we're just dealing with a single node. So for I in range world size, if I equals to the rank, current rank, then we create tensor, otherwise we create empty like tensor. Okay, so we still, got it. And then when you do all getter, they're just gonna fill it up. We're just gonna fill it up there. Makes sense. So we have, like, let's say we have two GPUs. One is gonna have data here and then empty. The second one is gonna be empty and data here. And then once we do all getter, all of them are gonna have all of the information. So that's what we need. Let's just see what's the difference between all getter and gathers arbitrary data from all nodes into a list. Similar to this, but for arbitrary Python data, know that data must be pickable and any CUDA tensors will be moved to CPU and returned to on CPU as well. Fair? Data from the local worker to be gathered on other workers. Group of the collective. Maximum size of the data to be gathered. Okay. Get the global group, get the rank for the group. What's the global group? So we get the world size, we get the rank for that group. Max size times world, that's the buffer size. Okay. So there is some memory pinning going on here. So all getter list _buffer all getter list _buffer if it doesn't have that attribute or blah blah blah, then we create the attribute by creating the byte tensor of this size and also CPU buffer of that same size, and we additionally pin it. And then we go and we grab the buffer, we zero it out, we grab the CPU buffer, we move the data to CPU, all of the data we pass, we first move it to the CPU, then we dump them as a pickle object, we grab the length, size of a header that contains the length of data, okay? And then header size plus data size. If that size is bigger than the max size, then we have a problem because we exceed the max size. And then header, we pack it as an integer. I guess this is big endian or something. We get the header and we store the data in a CPU buffer. And then what we do here is rank times max size to get the start. And then we copy that from the buffer into the CPU buffer, I assume. Just a second. But when do we actually put the data into this buffer? Wait. So this is 0 here. It's 0. We have the data, it's here, it's here. That's where the data is in. Okay, so we put the data into the CPU buffer. Aha. And then we copy from the CPU buffer into the buffer. And then we call all reduce on the buffer. Okay. And then we move it to the CPU. Or wasn't it already on the CPU? Wait. Wait just a second. Well, you can't do all reduce on CPU, so buffer torch CUDA. Okay, we create a CUDA. We create a CUDA. So we copy from CPU to GPU, we all reduce, and then we return to CPU. And then we have the results. We go through the world size, we grab the data, we unpack it to get and then we load the result. Got it. So this basically works as long as the data is pickable and of certain size. Makes sense? This should work. Either this or this. What do we want to use? Probably this. Let me just see again whether this makes sense also. This is much more efficient. All gather of a tensor list. Can we convert our data to a tensor? I mean, for now, this is gonna do the job. Let's go back to train. Probably more optimal because if we can somehow shoehorn our data into the tensor format, like tensor with strings. So distributed utils, all gather list, and then generations, and then this is what's the return value here. Result. Let's try this out, guys. This should actually work. This obviously needs to be generation as well, but for now let's just put it as a result so we can later, well, we can later do like generations equals result. Let's just check this. Does this make sense? Let's test this. Kick off the run. And wait for the breakpoint to be hit. Again, as a recap, we figure out what's the rank of this GPU, what's the world size. Depending on that, we take a certain subset of the actual languages we care about. We do a chunk, so we shard the work across the GPUs. So each of them is gonna just sample on a subset of floors. And then once they all have the data, we share the data between the GPUs here. And then we do some sorting, and then only on the master we log that to weights and biases. That's kind of how this logic works. Very neat. This can probably be further optimized, but it looks like a decent implementation. Almost here. Here we are. Grab the world size. Grab the rank. Rank is 1. Let's go. So all the way to here. So here are the target languages. And we enter here and just grab a single one. So this one is gonna work on Hindi Deva. So now we kick it off. We can kick it off, and we can also grab this one and kick it off as well. So now they're running on different GPUs. And now we can do the sharing. So this one contains generations only for Hindi Deva. If we plot it here, you can see that keys are just Hindi Deva. And if we go to the second one, that other one has keys. Oops, that's the wrong one. The second one has Turkish Latin. So hopefully after this all gather, if it doesn't fail, we end up with a shared, okay, it did fail. Because what? Probably too big of memory or what? Much bigger size than what we exceeds the size. Okay, so we'll have to specify the max size to like something a bit bigger. Why is this number so special? What's 16? That many bytes is, that's like 16K bytes, right? We have to go 48, we have to go 3x. Let's go 4x just for as a buffer. The calculator, 4 times 16,384, 65,536. Was that the number I gave you? 50, no, 65. 65,536. 65. 65,536. 65,536. Okay. Rerun. We failed the first time. Let's go and try this. Will likely never be bigger than this because these initial generations are super big. We can also dynamically obviously pass the max size. Just calculate how much this takes and then pass in that number. Let them run their own stuff. Wow, actually, guys, this is going to be problematic because this is only for 20. We have a ton more data than this. We have a ton more data than this, not just 65K. We have probably 10x this at least once we start doing without these breakpoints. I forgot about this for a second. So we'll see what the literature says, what the documentation says, what's the reasonable size here, how does the performance work in the background. But for now, let's just get it working in this particular setup, and then we're gonna see what happens then. We're gonna hit this one soon. Here we are. Run, run, nice. Result. Guys, here it is. Here it is. Shared data between the GPUs. Awesome. 21. 21. Because as soon as it's bigger than 20, which is 21, we break out. That's why it's 21. Okay. This works. That's a great result. Now, let's think for a second about what happens in the edge case when we don't have this. When we have actually 997 sentences, it's going to be like 50x what we currently have. How is that going to work? Let's go back here. So what this does, it allocates all of that memory. We zero it out. So CPU buffer. Okay. And then, so move to CPU, the data. Luckily, the data is already on the CPU, I think, for us. I'm gonna double check that. Then we dump it as a pickle. Then we pack it into the CPU buffer. We copy it into the buffer, which is going to go to the GPU, be reduced, and then retrieved to the CPU and then unpacked. Interesting. So pickled, data is being pickled, moved to a CPU buffer, then moves to the GPU buffer, then all reduced, then moved back to CPU, then extracted, unpacked, unpickled, and retrieved back. Okay, first thing, let me see these generations. So this is a dictionary on the CPU, obviously. We append, all of these should be on the CPU. All of this should be on the CPU. None of this, even when we run this, source tokens are moved to the CPU. And target, and so this is definitely on the CPU. And then these are also on the CPU, so this is definitely going to be on the CPU as well. And sample ID is, could this one be on the GPU? Yeah, this one might be on the GPU. So we might have to move this one to the CPU just to make it a bit more efficient. Sample ID. Let's put a breakpoint there and just double check this is on the GPU. Already, although tool list, this might move it on the CPU directly. Let's see. Excuse me. Let's stop this. Let's just quickly check that. And then let's understand what's the limit of the size here. I mean, 16K, that's definitely like a small memory. We can definitely pull in much more. I'm not sure why they set the default value to such a small number. That's what's kind of bothering me. For some reason, this is only this big. All reduce. Of the tensor. torch all reduced. Optimal tensor size. Okay, let's see. Sample ID is on CUDA, same as anything else is. So also if we grab sample net input, and then if we grab source tokens, this is also going to be on CUDA. But if we step over this, if we just start iterating, will the sample ID be, yeah, sample ID is apparently pushed. It's already moved to, and this whole list is probably already on the CPU. Let's make it temporary, oops, temporary list. This, yeah, this is already, so this moves it to the CPU already. So that means that once we end up here, all of these generations, all of this data here is already on the CPU, which is reasonable. Okay. So now let's see for the size. What do they say about the size? And also, let me think for a second. So we do have the same number. We'll always have the same number of lists, but they will be of different lengths. So we might be hitting this all-gather tensor if not the same length. Let me just go back to our implementation. I think we don't have any issues because we pack it to the buffer and then we all reduce the buffer. What's the start? Rank times the max size. Okay. Yeah, we don't have any issues as long as we don't overstep the max size. I mean, these all reduce operations sometimes work on top of terabytes or gigabytes of data, so just curious about the shape. Is there any recommendation there? So we ultimately end up doing all reduce, right? So gather ends up being just all reduce in the background. So all gather ends up being all reduce. Is there any recommendation here? buffer by tensor. It should be multiple of 8, that's for sure. Let's ask ChatGPT. Okay. Okay, so then let's make it just divisible by 8 or something. So what we can do is figure out what's the max. Let's go back to train. How do we, what's the size gonna be like? We grab the data, dump it onto the CPU, and then encoder length of encoder is encoder size. And we pack that together with header to here. Okay. So we just need to be able to place in the size of the data into that list, into that array. Let's see what this gives us when we call it up there, and how can we I need to force them to, we need to use the maximum value. Let's import pickle quickly. And then grab the generations and just print the length. Of this. Okay. And then save this, stop the run, and remove this. See how big this is going to be. Once we're done, let's see what's the size, and then we can see what to do, because if we start doing this dynamically, that means we have to have two syncs between the GPUs. The first one to share what's the max, and then that's gonna slow us down. So it's basically a trade-off between taking a bit more memory and slowing us down. We might be more bottlenecked on the memory side at the moment, locally, running it locally, so I might actually want to do it locally. Slow us down a bit, but share the max size so we can have the optimal size, as opposed to overshooting by too much. If that makes sense. See, we're running. It might take a while for this to finish. Okay, luckily we just have... Wait, how come we have only 13? Let's just put a breakpoint here quickly. What's the size of this one? Net input. Actually, just number of sentences. Let's see, sample. Number 40 sentences. And you're telling me that what? Okay, let's just let it run. Let's see until we finish what we get as the final result. There might be some errors here. Generations. Almost done. Turkish Latin. Huh. There's some issue. Key error, net input not found. What? During the inference step, it could not find the sample. Why? Let's see. Inference step. Train. Validate and save. Train inner. Intermediate inference step. Why would that happen? Maybe because I stopped it. Wait. What's going on? Sample. We go through the progress, which we got by grabbing the iterator for this particular language. Okay, let's run this again. There might be some weird distributed bugs that I'm ignoring. Let me see what people on Discord are doing. Okay. Let's go. Language. Split to get the code. Set up this one, and then grab the iterator, and then can I do something like length of iterator? Yes, I can. So it ends up giving me only 15. So something is off. Something is weird there. Okay. So I'm gonna put a breakpoint here. That's gonna be conditional. So sample not net input in sample. Will that even work? I don't know. Let's see. For now, let's just hit F5. Let's start running. Run again. Eval on Turkish. Debug console, subprocess 3.6, 5.5, and 5.6. This one does not print anything. Turkish Latin. It should work, guys. Let me see. Okay. So we stopped on the breakpoint for Hindi Deva because for some reason the sample is empty. Wow. Why would that ever happen? Okay. So now this is gonna completely fail. Okay, that's the failure. Okay. Huh. Rerun on train. Maybe that's because, wait, let me just quickly see. Dump location. Aha, maybe. Let me just delete this one and start from scratch. Rerun. We don't want a breakpoint there. We want a breakpoint here. If this happens, I really want to know about it. And then we're going to figure out why is that happening. Okay, I'm going to go grab some water, guys, quickly while this is running. Be right back. Okay, guys. I'm back. Let's see what happened. So we are skipping empty batch 14. Let's see when is the next. Okay, a single one was skipped. So here are the generations. Hindi Deva has 488. That's twice the amount of data we actually need. Huh. Okay, so it might be that, wait. Why do we have only half of the data? Okay, we're gonna figure it out, but let's wait for the second process to finish as well. What's the length here? 1 million something, okay. And then for the second process, let's see that one. For the second process, let me target it here. And step over. Okay, and what's the generations? Turkish Latin. Again, only half of the data is here. Huh. That's interesting. So we drop certain amounts of data on both languages for some reason. Let's understand what happens. Something with the iterators, probably some assumptions being made. By the way, let me just check my microphone is working as expected. Yeah, Rode. Do you guys hear me well? Do you hear any noise other than my sound? Let me know in the comment. Okay. So there's some dropping that happens. That's weird. And now if we try to all gather, obviously this is gonna terribly fail because the max size is too small. So what we need to set is, this is 1 million. Let's see, what do we get if we multiply 1024 by 1024? And then times 2, that's gonna give us 24 times 48, that's 2 million, like this. Maybe we can set the max size to be something like that. And that's, again, that's only a couple of megabytes. Because this is in bytes. That's fine. Now to the bigger problem. Why is it the case that this progress is dropping some data? Skipping empty batch. Interesting. So iterator, we grab the data for that one. Aha. Okay. Let me think. So in all reality, we don't actually have to do this logic with ranks at all, guys, because the validator itself will be sharding the data. So we can literally just remove this whole logic and just put this here and just remove this whole thing. Target lengths, nothing is needed here. We don't need this. We don't need this. Whoops, we do need that. So let's see, configs, eval, model, begin, target for keeping the context here, language code, iterator. So this one is going to iterate across both languages. Huh. Okay. And then here, so how do they do it in the validation? Let me just check. So this now should be better. So we'll be computing on all GPUs will be computing all languages, but just a subset of the validation data. And then we'll be pickling it here and passing in. Let me think. Let's go to validation. Validate. Let's enter here. We go through all the subsets. We create a progress bar with the iterator inside. And then here it takes care of sampling, sharding the data. And then at the end, we just aggregate everything inside of the validation step, actually. In the validation step, there is a task validation step, and then at the end, there is a data aggregation of the output. Okay, let's stop this. Let's rerun. The only confusing bit is why is it dropping samples? Why was any of these empty? We'll have to step into it once we get, let's just run this. And let's see where we start dropping data again. If we catch that same bug again, in that case, we are going to step into the progress, step into the iterator, and see what exactly happens on the low level that causes us to return back an empty dictionary as opposed to an object that contains the inputs to our network. Okay, well, while we're waiting for that to happen, let's just see what are the other tasks. Let me remove this. Okay, so this is that task. And the next one is, let's add more tasks to the GitHub project so that we have good first issues and stuff like that, so beginners can just come in and contribute. Okay. There is apparently some data for Serbian. Let me open up my LinkedIn quickly and let's wait and see what happens here. Okay, so far we are not hitting we're not hitting any issues anymore. We're not hitting any empty. So it was probably due to the fact that I didn't have, yeah, the second part of the data was not being consumed. And so that was confusing the iterator. We were misusing it. We were not using it properly, so to speak. Okay. So we do hit empty on some occasions for some language. Is this Turkish? This is Hindi dev as well. So how is it progressing then? It's the other process. Okay, let's see. Skipping empty batch. Okay. Super weird. So 14 is the index. We're gonna grab the, when I equals, gonna set this to here and set edit breakpoint when I equals to 13, so we can catch it before. That's gonna be the next thing we do. Now let's just continue and hit the breakpoint down there. Hit F5. Here we are. Let's step over this. Okay, so we see now almost 2 million. Let's see what's the data we have. We have for both data sets 447 for Turkish and 488. Let's sum them up. Let me just sum them up. I'm not sure how the debug console is going to look like. So for Turkish, we have what? For Turkish and for Hindi. So for Turkish, Hindi, 488. For Turkish, 477. And then let's switch the process. Let's grab the other one. This one has, for Turkish, 520. And for Hindi, 509. So in total, we end up with 997 for Turkish, which is the right number, and we end up with 997 for Hindi, which is the right number. So what's the thing? Why did we... So if we now do the all gather, this should now work. Okay, we have the result. Turkish. Wait. Let me just see whether this worked. Generations. Oh. It didn't really aggregate the way I expected it. It has Turkish, and then here it aggregates more data. So it's like not the right type of aggregation happened. Let me see. How did this even work? It seems they have the same keys. But they're just, okay. Interesting. So we passed in generations, which was a default dictionary. Aha, okay, so it's just confused. The all gather is just confused. Okay, let's see how we can fix this. Index 14, empty dict. Here we have to figure that out, and we have to figure that out, and we have to think how to make this aggregate correctly. I mean, we can always post-process. That's something we can easily do, guys. We can always post-process our data and get it into the right shape. But maybe let's see whether we can directly get it into the right shape here. So they pickle, and then they copy. And so because it's a dictionary, dump the data there, put it here, copy it there, then all reduce. So that's why we end up with two separate dictionaries. Okay, so what we want to do is well, we can maybe just post-process. I don't see a different, better option here because we cannot communicate between the two. What could be the solution here? We have a language and data associated with that language. And we have a second one, and then we want to aggregate. We want to gather those across the GPUs. What can we do? Okay, let's just try and post-process. If I understood it correctly, the last time, once we call this, then to get the generations, we'll actually want to add to the dictionary. So we want to go for in result, we grab the dictionary, and then for keys, I mean for key value in this, we want to basically append, right? Because okay, but generations needs to be first set to none or something. Okay. Let's just create a brand new default dict, and then we keep on appending, and then at the end, we want to assert that for key in generations, assert that the length of generations key should be equal 9 and 7. We got okay. And this should be now good. Let's rerun and see what happens. Until then, I just have to read some posts which are in Serbian, so it will not be super useful to you guys. I'm looking for some Serbian corpuses, so I'm just looking at this post I wrote down in Serbian. Maybe I can translate later, but I'm not sure it's going to be proper translation, so I'm going to just read in Serbian for a second. Actually, this is Croatian, but they're pretty much the same languages. Okay, so they're basically now just fine-tuning some multilingual models for regional languages because they don't have enough processing power. They're mostly focusing on data, so they're looking for somebody who has compute, and then they help them out with data. They have 13 billion tokens for now. Or I guess this is Croatian, Bosnian, and Serbian. He'd love to combine those with Slovenian, Macedonian, and Bulgarian. He's interested in collaboration. Okay, sounds good. And then he says for parallel corpuses, I need to talk to this person and this macaque parallel data sets. So I'm going to see what options we have at disposal. I think we're still waiting for the compute to process here. Let me just see what's going on in VS Code. It's still running. I think it's going to interrupt me as soon as it's done processing. It's very slow. My computer is glitching when I'm running all of this and streaming. Whoops. And here it is. Wait, why didn't we stop when I was 14? Now it's too late. Because this was a modified, fuck. Okay, wait. We have an issue. I want to, okay, let's just for now test, let's test this one down there. Cool. Let's do the all gather. And let's see the generation. So result contains, as I said, 2 dictionaries. And this dictionary contains 2 languages. So we just append those here. We append them here. And now we have them. And now, I should have called extend. If we just append now, what do we get? So we have Turkish. We're gonna end up with a wrong format, guys. We're gonna end up with a very weird format. As you can see here. As opposed to having just a single list. Okay, I think we need to do extend here. And this should now work. And also, let me just, either way, I have to stop it because we skipped the breakpoint of interest, which was here. And if I'm gonna put it again and say, hey, when I is equal to 13, please stop. And this should now work. Let me go and rerun this while I'm addressing the question here. Not for Serbian, but I'm gonna translate this in a second. Let me just, or I can just show you the translation. Let's go. Why are you? Okay, I definitely have to put a breakpoint here. That's running in the background, so I don't care. I'm being inefficient at the moment because either way, I'm now just writing this message. Let me rerun train. Let me just wrap up this. So I'm gonna copy the name of the channel here, copy the link. Okay. Okay, reply. Let me show you the translation. This is the only, I think, bad piece of translation. Everything else looks decent. It's actually a fairly decent translation. Okay. Let's see how this is progressing. Let me put a breakpoint somewhere before this starts. Okay. We are now at 3. And the second one is at 5. Continue running, continue running. Six. Why are you stopping at 6? Okay, I probably have to remove this and put it back in. Run, run. $13. Okay, let's go. And which language is this? That's the right one. That's the language we care about. That's the language that was problematic. Hit F5, get to here. This one is 13, but we don't care about that one now. We now care about this one. And let's enter. Are we at the right track? Wait, what's I here? No, I is 7, so we don't, wait, we can just step over. Okay, now I is 14. Oh my god, we skipped it. I hate this. I hate this. It's happening for Hindi Dev. So I have, oh my god. Super hard to debug this because I have 2 processes. So I have to specify additionally. I'm going to specify if this is the case and the language code is Hindeva, then hit it. So if this is the case and language code equals this, only then stop. Otherwise, I don't want to hit 100 processes. So if this is true and language Hindeva, in that case, stop. Because on the next iteration, I'm going to hit the right one. Okay. Sorry about this, guys. Just sending some DMs on my side. And let's see when we hit this. Okay. Let's see. Right. And this is it the right language as well? Yes, it is. Let's go. Let me just switch to the second one and just progress it. Why did it stop here? because it also has, okay, let's just see which one is gonna be problematic one. Go here. Enter. Run. Enter here. Enter it to the iterable. Here. Let's enter. Next. So what I'm looking for is why are we next data, next index, data fetcher, collate. What's the sample? The sample is empty. The sample is empty, so the result is going to be empty. And then we return back to empty result. Clean the empty dictionary and retrieve this back. Why did that happen? Yield. Skipping. Interesting. Okay, let's go to the second one. Okay. Get the item. How do they protect against this in their other functions? Why am I the only one to hit this issue? Hi Smith, how are you doing? Hi Kugo, thanks a lot for the compliments. We're trying to debug why this sharding of data during eval is retrieving back empty dictionary for one of the languages, for one of the processes, for some reason, which is weird. So index, hey Ali, this is scary. Index is what, 73? We grab the target. Okay, let's see what we have. If we just enter here as well, data set. This is the memory map data set with 997 as expected. And so we select the item to get that particular sentence. And then we have the token. This token is just the language token for the source language, I guess. So we prepend it to the existing item. And so we just end up 534. Before that, we're gonna prepend it with the language token, and then we retrieve it back. We do the same thing for source. So we do the same thing for source. Again, we grab the pointer and the size for this index. So size is this, 65. and pointer points here. We convert this to buffer, and then we return back the numpy array. With this offset and this size, we fetch that many elements. This is just how it's implemented in the background. What's your squad personal record? No, that wins the medal of the biggest aggression on this stream. I never focused too much on one rep max. I was mostly doing always 5. Like if I couldn't do 3 or 5, I would not be doing the weight. But I was doing 125 S to grass squats, 5 sets, 3 reps. That was my peak. My brother lifts around 300 kilos. He's much more into optimizing for the weight, for the peak. If false, okay, let's go. So we're now in the language pair. We fetched from the underlying memory map dataset. We fetched the data. Yeah, he also deadlifts around 300 without like wearing a belt or anything, or waist. How do you call it? Is it belt or waist? Okay, and so now we have example, and belt, and then we go back here. Possibly batched index. What's the value of this one? Not defined. Why are you not defined if you're here? What? Okay, 5 of these. Could it be that in the last one we just had a empty? Okay, we're gonna see what happens here. So now we collate the data. Now that we have this data, we collate it. I guess that's less important. What is important is that we have the data. And now this is good. We pin it, and we can now retrieve it back. Yield the object. Why are we here? Okay. Wait. Why do we skip those samples? What's going on, guys? Something is weird. Something super weird is going on. We just gathered 5 samples and then we skipped them. What? Why? Or maybe I have to put a breakpoint here as well. Sometimes once we exit, I don't know. Let's just go here. Let's just go here. Let's aggregate the generations. Let's see what happens here. This now looks good. Aggregate. Done. And the generations now look decent. That's it. This should be 997. And the other one should be 997 as well. So that looks good. We passed the asserts. So everything is working, apparently. But there is this weird glitch that happens. That I cannot seem to explain. Let me see how close are we to hitting this max size. I'm currently at 2 million. This one is almost 2 million. But if we analyze the actual generations, I doubt we're gonna ever have longer ones because this is just gibberish text. It's never gonna be this long. So we probably want to minimize this max size of the buffer later on. Okay, we are almost done with this function. We are almost done. I really want to better understand the data sets. This is gonna help us so much later down the road once we need to debug stuff, because I've been organically internalizing all of the code from this code base. I think that's going to help us tremendously down the line, debugging stuff. Let me leave this here. Okay, something like that. We can remove this or just leave it there for debugging purposes. And then master is gonna do the logging. We can do this only here. And then we won't have to do this additional post processing. Okay, that's now all nice and good. The last thing to understand is this. Again, whoops, why did I remove that? Why are we hitting empty sample? Let's put this to 12. And let's deeply step into this whole logic. So I 12 and line code hindi deva, and let's run. So I'm going to step through every single detail of the code. So iterator is around length pair. Ultimately, at the bottom of it, we just have memory mapped data. Because that's the output of the data processing pipeline. We end up with a bunch of this bin files which contain the tokenized binarized version of our sentences, and then we load from there using mmap dataset, and then we wrap it up. So like maybe one thing might be worth it before we get to here. Why not? This is going to be the last task here. Let's go to train. Let's find the dataset loading, which happens on the load checkpoint. So here is where the dataset loading happens as well, epoch iterator. Let's put a breakpoint there, and let's exactly understand what happens with the data. Even though this is a train dataset, we are gonna understand the underlying process. I know there is some sharding. Maybe there's some bug that happens that we later hit in this. I don't know. Just some assumptions. Okay. Let's go. Enter here. load checkpoint. Let's see where the interesting stuff starts happening. Suffix. Let's just go here, skip over all of this, skip over all of this. First launch, true. Okay, skip all of that. We don't care about that. We care only about the epoch iterator. And that one happens here. Okay, and then enter. So here it is. Get the train iterator. Load the data set to true. And pass through arguments. Disable iterator cache, true. Why would we set that? Because load checkpoint, we called it with, apparently we called it with disable, has sharded data. If this is true, then we disable it. Don't cache epoch for sharded data sets. Okay. Let's go. Enter. If loading. So we first load the dataset, similarly to how we've done it above here for the task load dataset for the validation. So we load it, and then we pass that data into the batch iterator, and then we just basically do this dummy batch stuff. Let me see what happens here. Train subset, epoch 1, combine set to true because no argument is passed. We just use the default one. Data selector none, TPU should be false. Okay, let's enter here. Here we are. Now we are in the, this is gonna be a long journey to the center of the earth. Jules Verne, or however you pronounce his name in English. Okay, data sets are currently these three because we've loaded okay, so again, this is the task. The task owns the data sets. Estimate the global pass epoch. What happens here? If any of these are none, then we return none. Okay, so this is none. Loading data for train. Get the memory usage. And then we go and delete the data into the split data sets, and then if we have multiple splits, okay, which we won't have, I think, just we have a single one. Training true, epoch. Okay, let's see what's the keyword arguments here. Data selector and TPU. Okay, let's go. Load sampled multi-data set. Let's go. Load the splits of the data sets. And then at the end, we end up with data sets. We just wrap them into this and we retrieve it back. So this is where the main logic will happen. Load the split data sets. Load the, so we go here. We grab language pairs and the data, of which we have 28 shards. And we have 202 languages in general, but here we just specify 2 that we care about. Okay. So we return that back. Okay, let's go. Split the number of shards. Get the paths. Get shard number. So we get the number of shards for each of these data sets. and then we get the dataset key, main English Latin to Turkish Latin. Okay, if this exists here, then we fetch it. English Turkish. Else if here, else if here. So we just end up collecting the shard information for these two, and we add them to the split, which was train, and we go back. So that's it. We get the shards, get split number data shards, get data paths. Okay, so now we trade through the data paths. Split the paths. Has sharded data, yes. Length token specification, language directions. Okay. Similar logic happens here. We get the data path. We have the paths, the epoch, the shard, and we get how many we care about here. Let's enter here quickly. Number of shards 28, get the shard ID. We get epoch, shard 0. This is the 0th shard. And so we add this with this data path, with this split, this source language. We grab the dictionary, same here. We grab the dictionary, and that's it. Now we continue. Key, data path, and we add it here. Okay, so interestingly enough, we just bring the last shard, the first shard. So how do we now combine that here? So we just have the one shard there, and then we say combine, and then we go through the params. Okay, let's go inside here. Let's enter it into the load data set. This one is going to load us the data. I'm just curious how it's going to figure out all of the other shards. Is it going to compute it again or what? Upsample primary, left path source. Okay. Get the source language token. Get the decoder language token. Okay, main English Turkish. And then we just skip over all of this and we load the language pair data set. Data path, just a single one, split, source, combine, data implementation should be mmap. It's going to be inferred, I think. Then we have all of this, so no mention of the sharding. Let's go inside here. Load the language data set. Because I think we're gonna do what? We're gonna do both directions here somehow. Is there a for loop here? No. Load the data set. enter here. If the split equals train, if the train is in here, if the split exists, grab this file name. Okay. Dataset exists. Data file path, given the path, this is gonna give us the bin. Yes. And then we asked if this exists and this exists, if the bin, okay, and this will say true. So because of that, we grab the prefix. And then if there is a train prefix, we'll load truncate source. Train prefix plus source dictionary. Dataset implementation still not inferred. They're going to use the header information to infer that this is mmap. That's how this is going to work. So this is the source piece of the English Latin to Turkish Latin. Let's go load truncate source dataset. Not clear what that exactly means. Full path is here. So let's load the data. And then they say, this is multilingual dataset manager. Load index data. This is the dictionary. This is implementation none. Here, let's go. Path looks like this. Get index dataset to local. Index to index. So we get the index path and we get this one. Assert they end with the right suffixes. Then we grab the local one. We assert this is the same. And we return back it. Okay, so this is it. This is the path K. Implementation is none. If it's none, then you infer it. And then this is how the infer part works. If this path exists, which is gonna check again for the index and data, then we open up the index file. We read the magic and then infer this is mmap. And then we call, so load data, load truncate calls the load data. We are here. Make the data set. Here's the path. I'm still confused. How do we load multiple shards? I've never seen that. I'm gonna figure it out now, I guess. Implementation, fixed Lua indexing, whatever that means, and dictionary. This is again source dictionary. Let's enter here. So because we are mmap, we pass in this and we create the mmap. The mmap does what? Do init, grab the path. This is the prefix path. We grab the index and then we create the index here. We create this and then we are in the open. We open up the index. We read that stuff. We unpack, length offset. We warm up. I don't remember what warm-up does, but like this is probably maybe a bit too much. Okay, so it just reads the stream here, okay? And then memory map to this to get the buffer, memory view. Then we convert it to get the sizes, because this is again length and offset. So offset is from the header. The length comes from getting that information from the header. And so now we know how much we need to read from where and which type to get the actual sizes, which is information in this index file, which tells us how much each of the sentences from our dataset shard are long. That's that information. And then we construct using the sizes and the offset and the length and all of this. We now grab the pointers. Okay, so that was that part. We constructed the index. We have the pointers and we have the data. Now we warm up the data path file. Again, similar thing. I'm not sure why we're doing this and what is stream at all. So we'd open this up as this, then we read it. What happens when we do this, I'm not 100% sure. Just an optimization detail. And then we have the binary mmap and the view, and that's it. So that's what this does. The index dataset make dataset. That's what we got there. And then we say we loaded that many examples from here. We append it, and if not combined, if this is false, then break. And then if length, here we return back that data set, okay? And then truncate the source set to false. Load truncate source. So why are you calling it truncate if this is set to false? Okay, whatever. So we just retrieve it back. So we are done with the source part for the English to Turkish. Add source prefix tag is set to true if it's a trainful data source. Okay, so here are the different types of prefixes. Is this coming from mining? Is this coming from back translation? Or is this coming from... where is the primary? I don't see the primary. So this is not going to be the same. Well, this is never going to be... Yeah, I'm going to skip all of this. So appending will not happen. We append the dataset from the source, and then we append load data, train prefix, target dictionary implementation. This does the same thing as, I think, to what we've seen before here. So load truncate source was calling the load data in the multilingual data manager. So that was the load data, and now we do the same thing. We call load data. We're still in the data manager, so that's the same function. Let's just enter in there. Now we don't have to repeat the whole process, but we load Turkish. We load Turkish and we're out. So now we have Turkish, and now we have, so we have two mmap. So these are the, so this is like the bottom level of the whole abstraction, right? We are literally dealing with bytes. We are dealing with pointers. We are dealing with bytes. We loaded the data, and then we say we loaded that much for English Turkish. Okay, and we are now where we were here. We've done single pass, and that's it. And we make sure the lengths are the same for source and target. This is again load language dataset. And we were passing through these loops here, because we are dealing with if split equals whatever train is. So this is for the train split. For the validation, we go through this branch. Okay. So here are the data sets. If prepend, if align, otherwise we return back the mmap data sets. So these are the mmap memory mapped index data sets. Align is just none. Let's go. So now we are back in the load language pair data set. So here we are. We ended up with that data. And now let's see what else happens. We now call some transform function, which we passed in for before. Let's see what that one does. So what it does is it grabs the data set and then calls this thing, which I don't know what it is exactly. Something that's defined up there. Okay, let's put a breakpoint there. Let's put a breakpoint here. Let's just keep on stepping in. Keep on stepping in. Okay, so how did we end up here? We ended here by passing the mmap dataset to here. This might be the deepest debugging session in the history of streaming on YouTube. Fun. After this, we're gonna understand every detail of the dataset loading. Okay. What happens here? Replacing BOS EOS. We skip that. If spec is none, it's not. Otherwise, we get the encoder like token. Let's see what it does. Get the language token for source. Multilingual. I've never entered into this one. While we are so deep, maybe it might be fun to just go here. So if the spec ends with DAE, which is the denoising autoencoder, nope, nope, nope. Otherwise, we grab the token styles. Aha, so this just returns back the style for the token, which is going to be like this, and then we just pass in the language. That's how we get English Latin. And then what we do is, again, we passed in, this is the get encoder length token. Here's the length token, and then we get the index. So given the length token and given the source dictionary, if the source lang is existent, then we let's just enter here quickly. Get the source. Okay, dict. And now enter here. So we just index into that with that particular, and we get the index. Okay. So we didn't have to do that really, but nonetheless. And so if token exists, so what we do here, as you can see, this is what the source dataset transform function does. So we now loaded that memory map dataset, and now we are prepending to each of those sentences, which are tokenized. We prepend them this particular language token by calling this prepend dataset, which is just going to be, what's this base one? This is just some abstract fairseq one. Okay, just some abstraction there. We save the token. If it's not none, we modify the sizes. These are the sizes we got from our index. We add +1 because all of them are now going to be a bit bigger. Okay, so that was it. That was the source one. Let's see how we transform the dataset, the target one. I think we also just prepend the target token there. That's all that's going to happen. So we're going to enter here, and we're going to get this token. I don't want to go through the same procedure. This is just for this language, Turkish, and then we prepend, and that's it. So mmap, and then on top of it we add the, maybe we should literally document that somewhere. I'm gonna document that somewhere. So on the bottom of the stack we have mmap, and then so dataset construction process, dataset construction. Let me share this with you guys. Process mmap loads from bin and index. If this is, was this the suffix? Let me quickly check for scopes. If we enter here, we have the bin and IDX. Okay, we have the bin and we have the IDX. Gathers, pointers, bytes. Then we have transform, prepend language tokens to both source and target mmap. That's where we are. Let's go. And we are now where this was none, so we skipped this whole process, and now we are still in the load length pair, and now we have to just wrap them up into this length pair dataset abstraction. That's all we do. Left pad source true, left pad target false. So this is going to be left padded. Okay, that's probably important once we start loading the data. I'm going to be padding it from the left. Whereas this is going to be padded from the right, I guess. Or actually, yeah, let's see. Align none. Language ID none, language ID none, pad to fixed length none. Let's enter this abstraction and see what happens. So here we assert that the padding for the source, this is going to be like, this is a tautology because we're using the same underlying dictionary for both the source, which is the SPM 200. Okay, here we assert that the length of the source and this one are the same, and then we basically add them there, and then we grab the sizes. Again, those are the sizes we saw before, +1, because we prepended the tokens. And then we do what? We go, if this is not none, as it's not, then we grab these, we v-stack them and transpose them. So we get what? We get, currently we have, is this a tensor or like what's the type of this object? This is an ND array. So what's the shape? The shape is, it's just flat structure with 1,000,000 something 200 sentences, 1246, and this is 8. So we expect to see 20 and like 46, 97, 20 and 97 after we v-stack them. In sum, but because we v-stack them, we get something like this. Okay, so we basically create 2 columns. Save that. Left pad. Okay, nothing happened there. Shuffle should be shuffle, true. Input feeding, I'm not sure what it is. What's input feeding? Create a shifted version of the targets to be passed into the model for teacher forcing. Remove EOS from source, append EOS to target, align constraints, let's go. If number of buckets bigger than 0, it's not. Otherwise, pad to multiple. I'm gonna put a breakpoint here because this is gonna be our underlying data set, so we're gonna be fetching data from it using the get item. Length, collateral, number of tokens, filter, prefetch. Okay. Let's go. Pad to multiple 1, fixed. That's it. So that's it. We just have an abstraction around our mmap datasets, which are basically, okay, so we have length pair abstraction around the above 2 datasets, which are of which class, their class is basically prepend token dataset. Let's go. I should probably rename this stream a bit later so that people know exactly what we've been doing. This is gonna be like a good video in and of itself for understanding fairseq data loading and understanding how we were basically trying to debug some issues. So like it's gonna be a super useful stream for anybody who wants to pick this up later. Okay, here we are. We were here, we created the data set, and now we just return it back. That's gonna be that's the load the dataset function. Okay, and now we repeat that same thing for the second language, which is going to be, I guess, Hindi. This one was Turkish, right? This is going to be now Hindi. I'm not going to repeat, obviously, the whole procedure. So I'm just going to say disable all the breakpoints except for this one and run. And you can see the output here. We loaded 234,000 examples for Hindi. And that's it. Now we have a list of these data sets. And we go back. We get back up. So load sampled multi-data set. We are here. We loaded them. And now we enter here. So now the question is, how do we sample between these two datasets, right? Because now we have two different datasets underlying here, and we have to somehow sample. So we can maybe upsample and focus more on one of them. So epoch datasets, data param lists. We enter here. I'm familiar with this code, but let's quickly just go through it. So get the sampling ratios, get the trained dataset sizes. Okay. Get split number of dataset shards. Let's see what it's gonna do. Get trained dataset sizes. Number of shards, 28 and 1. And we end up with, So this is what we do. We fetch the data sets. We have the number of shards. And now get the shard index. This is the length of this one. And we append. And now we can go back here. And we have exactly the sizes that we've seen previously. So basically those were stored here. Length of data set. We just grab the length of the data set. That's it. Now that we have the dataset sizes, we pick the sampling function, and if it's not none, which it's not, we grab the sampling ratios. We're just going to use the temperature sampling. So we sum it up, and this is 1.3 because that's how I've set it up. And so we get back with the sampling ratios right here. So this is how much we're going to focus on the first one versus on the second one. The first one is bigger because it also has more data, and because I've increased the temperature, it's a bit more closer to each other. Otherwise, if the temperature was 1, this would be even bigger difference. So sampling ratios. we log the sampling ratios. We assert that's the same size and we return them back. Okay, so now we do additional abstraction here. That we're gonna do is we're gonna wrap them into the sample multi-dataset with the sampling ratios, with the collate format of single, whatever that is, and split is train. And this shared, I'm not sure what these two are, like just quickly enter here. This is just some enum for the format, and call later, return not and not. This might be fun to see how this one plays out. Hit F5, we're here. Extra data is none. So nothing's gonna happen here. Replacing. So this will return, I guess, false. Okay, enter here. It's set to true. So this one is, again, just a fairseq dataset. Shuffle, true. Get the keys. So these are two language directions we care about. Get the values, which are going to be the actual lang pair datasets. So again, let me add this to our logic here. So we have this one wraps multiple and assigns sampling coefficients, sampling ratio to them. For example, we currently use a temperature of 1.3 for Turkish and Hindi. Okay, let's go back to where we stopped. So we assign this. This is going to be train. Eval key is none. Collate format is single. Okay. Current indices, let me see what this means. Is the data item I in this sample dataset, namely, data item I is sampled from the kth subset where this accumulated size is, okay. This is just some sampling logic. Reset cache properties. Clean if not none. Okay, just set some default values there. Set up the sampling with the sampling ratios and virtual size. So if sampling ratio is none, it's not. If it's not an instance of the array, then we wrap it into the array. We have them here now saved. And then virtual size, if virtual size is none, then default virtual size function. Okay, let's see what the one does. And then if callable virtual size, then we call it with our datasets and with the sampling ratio. So let's see what happens. We call it, we grab the lengths, whoops, we grab the lengths. Here they are, the familiar numbers we've seen before. If the ratio is none, it's not. Otherwise, we grab the sizes, we get the largest index. This is the largest dataset, the number 0, which is Turkish. We grab its ratio and we grab the largest, and we grab its size, okay? And then the virtual sizes will be, we go through the ratios and we just divide by the largest ratio to normalize it, I guess. So that means this one is going to be 1 and its size, and then the second one will be normalize. So we have here, so yeah, so this is effective. Aha, got it. Super cool. Super cool. So this is the virtual size. So basically after we change the temperatures, we end up having not 200 or something, which was the original length here, 234. Instead, we end up having as if we had 340 sentences. We sum them up to get the virtual size, and then max scale up, and then we get the max size, 2236, and this is, okay, just a second. Let me see here what they've done. So we have the virtual size, and that's apparently shouldn't be bigger than 1.5. Max size 2236, virtual size 1602. Okay, we are below. So if we are below, then we return back the virtual size. Otherwise, we return back the max size. It can't be more than 1.5. Interesting. Fairly arbitrary max scale up, but okay. Let's go. That was the virtual size. We now exit. It also computes the virtual size of the data set. Now that we've potentially upsampled some of the length direction subsets. That's kind of the learning there. Let's continue. Set the epoch in this sampled multi data set. Let's see what happens there. We call this super class of the sample, which is just a epoch listening class. Interesting. This one just passes. Epoch listening. Why are we epoch listening? Interesting. Okay, and then we go through the data sets. If it has set, then we call it. This is the length pair. So we call it. Let's see what that's gonna do. Again, pass, and then pass. Nothing happens there, apparently. Set the current epoch. Establish virtual datasets. So this might be important. Let's see what this one does. If sample ratio is none, it's not. Reset cache properties. We've done this before. So just ignore that. Start time. And then generate a weighted sample of indices as a function of the random seed and the current epoch. Oh my god. What a session, guys. What a session. This is crazy. We get the class name sampled multi-data set. We encode it as UTF-8. So we encode it as UTF-8, and we then digest it to get the integer, and then do modulo, and then depending on the seed, that's also with the modulo and current epoch, we get the current random state as a function of the random seed and the current epoch. Clean if not none. Cumulative sizes. What does this do? Okay, again, the same thing. Okay, let's go get virtual indices. Random. Let's see, let me just see where we are here. We are in the set epoch, which is the last function of the init. We are almost done, almost done. This is very important. This one is virtual indices, passing data sets, which are the length pair data sets, and sample ratios, and virtual size, and random generator. Okay, so we get some get counts, sizes, and then ratios, sample ratios divided by the sum to get the actual ratios, and then to get the in dataset indices. So given these sizes and given these ratios, we get some dataset indices, and then we call get counts. We go through the sampling ratios, which again, these sampling ratios are, as you can see here, actually normalized. Okay, so what we do is we go through the sampling ratios and we multiply the virtual size by them to get the actual counts. Right, we get the actual counts. Here are the actual counts. We already got this number before, so we didn't have to do this necessarily. But okay, and then virtual size minus the count is a diff. Assert diff is bigger or equal than 0. Okay, and then we choose this many according to these ratios, whatever the length is. We choose to index 0, and then we go through the indices and we increment the counts of I by 1, and that's it. Okay, because there was some small difference between the counts and the virtual size, which is the desired size. We bumped up one of them by 1, such that we end up with the right count. Okay, just some numerical stuff. Let's go back here. And then uniformly sample desired counts for each data set. If the desired counts are large, sample with replacement. A random choice in data set. So we go through the counts. This is how many we need from each of them. And here are the data sets. And then we random choice. Okay, let's go inside here. Get the data set and the choice size. We get its size, and then we say choose this many we need. And replace only if the amount you asked for is bigger. And then same here for the second one. Choose that many, but the actual size is smaller. That means we're going to sample with replacement. And here are the indices. Okay, so that means even before we started, we have a set of indices. Okay, and that's going to be changing per epoch, because as you saw, the random generator is a function of the epoch, of the current epoch. So let's go up. Those are the indices. We're almost done here. Get virtual indices. Now we have the indices, and now we do what? We go through the data set and we grab the sizes, virtual size of per data set. And then we convert those into int 64 for some reason, and then we do cumulative sum. Okay, makes sense. And then we assert that the sum is equal to this one. Just some asserts. And then we do horizontal stacking of these, which ends up giving us all of those different data sets. All those indices being stacked together. Okay, fair enough. Almost done with establishing the virtual data sets. We now have the indices. We store them there. These are the current indices. These are the sizes. This is the size per data set. We get the raw sizes, which are a bit different. And virtual size, sample sizes. Okay, we print something. We say raw sizes are these. Resampled a bit different. Okay, and then if it's not none, upsampling ratios and virtual dataset established time. Looking good. So that was the setup epoch function. We're done. We're done. We're done there. And we retrieve back. So now we have this multi, okay, got it. So that one basically virtual size of the dataset. Now that we have potentially upsampled, it pre-computes all of the indices for this particular epoch or the virtual data set. That's what it does. Okay, after this, if we don't understand where I'm getting, after this analysis, if I don't understand why I'm getting an empty dictionary while I'm running eval, it's just gonna be mind-blowing. Looking good. We just have a single one. We go back. We are done there. Now the weird part is, why do we only have a single shard? All of this was just on the 0th shard. We have 28 shards for some of these languages. Why would that be? Why would that be? Huh. Could that be because... that would also explain the poor performance we got. Could that be because... Let me just open up that question here quickly. But we only loaded data from shard 0. Why? This is basically done. Almost done. Just trying to understand why we return empty dictionary at one of the iterations for Hindi. Okay, these are going to be some of the next steps. Let's go. Now we have the task batch iterator. We grab the data set that we loaded up here. So again, this load data set was saved, all of that in the self data set of the task. And now we grab that data set again. We have the max tokens, 2048, batch size set to none. Resolve the max positions. For the task, the max position is 512. For the model, the max position is also 512. and we have max tokens 2048. Resolve the max positions. Okay, the one returns us 512, 512. Ignore invalid, yes. Required batch multiple 8. Seed plus epoch, so seed changes every single epoch. And then I literally probably caught a bug because we're not using all of our shards, which was a very, very productive analysis if that's the case. So if update else this, else the common seed. So basically if this update ordered indices seed, otherwise we just pass in the default one. I think this is gonna be 2. So this is false, and because of that we return seed. Okay, number of shards. If this is set to true, shard batch iterator, then we get 2 shards. And then shard ID is gonna be whatever the rank is for this one. Number of workers 1, epoch 1, data buffer size, I have no idea what it is. Disable true, skip remainder of the batch, train with epoch remainder batch, no, don't. Grouped shuffling false, update epoch iterator. Okay, let's see what that's gonna do for us. Hit F5, enter here. Where is the second process, by the way? Where is the second one stuck? The second one is still stuck there. Oh, poor. Okay, let's enter here. Now we are in the get batch iterator of the task. So it's obvious that we only picked up a single shard, which means no matter what we do here, that's gonna remain a fact. So we have to understand why that happened. Okay, this is empty. If it's round robin sampling method, which it's not, we are using temperature. In that case, create fetch sampler function. Let's see what this one does. We return back this one. Construct batch sampler. We're gonna see what that one does. And then we call iterators epoch batch iterator, which is data iterators epoch batch, a multi-epoch iterator over class. We're gonna see what that one does. We're gonna see what, I'm curious about frozen as well, first as well. Next epoch iterator, all of these are gonna be interesting to understand. That's it. Okay. Let's go. We called the data set and we called its collator as the collate function. Construct batch sampler above. Seed is going to be 2, number of shards is going to be 2, shard ID, epoch, skip reminder, yes. Enter here. Okay, let's go save those here. Frozen. If it's not callable, then okay, what's the frozen one? None. Let's go. This upper limit here is to prevent people from abusing this feature in a shared computing environment. Interesting. Buffer size set to 0. Why? Because here we don't even pass a buffer size. So buffer size set to 0, and they just basically hard code this in a very subtle way. Whatever buffer size is, I have no idea what it is. Disable shuffling, false. Skip true, group shuffling, false. Epoch, shuffle. Support prefetch. That's it. So we then, at the end, we pack our data set. We pack our data set into iterator. That's how it works. So finally, we wrap it into this. Whoops. Wait. Let me delete this. Okay. Let's continue. This is our epoch iterator. And then we have just this last thing. First batch of the batch iterator is going to be what? How does one do first batch? It's just a property. If this is 0, we've never hit that one explicitly yet. So let's see, now we're gonna hit it probably. Okay. Frozen batch. If it's none, which it's not, how did we get that one? Wasn't this none before? This is weird. We've never hit that before. In that case, we collate. We go through the frozen batches. We collate that. And we return it back. Okay, I have to do one thing again. I have to disable everything and just see what happened here. Here, so disable everything except for this one. And disable everything except for this one. Stop. Let's quickly see what happened there, because I was fairly sure this was none. So when did it get assigned to anything else? Let's see. Okay, this was very, very productive analysis. I've never understood the data as good as I do now here. Okay, so batch sampler, is it callable? It is callable. So that means this is going to be false, and that means we're going to return none. Yes, exactly. We return none. But let's go, if I change the process, maybe there was some thing happening there. If I change this, this should also be none. And it is. Okay, so when did that thing get anything else than... Okay, let's see. Let's see, we just step through here. That's it, we exit, and we're now here. So first batch of the iterator. Maybe there's something that happens in this one. No, not implemented. Return the first batch is dummy. Okay, so that's not the case. So let's see. Let's go back here. First batch. This is the group batch iterator. This is the epoch batch iterator. Epoch batch. Okay. So the first batch is going to be here. Aha. Okay, so we enter here, but this one should be none. What? What, where, how? How does one change this without me noticing that? Where is it called? It's called here only. It's called here. We're right there right now. Here as well. Here as well. Here is set to none. And here it is set to something. Okay, in the init. But this is, wait, we are not a group epoch batch iterator. So that means we never call this. Am I the only one confused here with this? When did we ever update the frozen batch? Okay. And now all of a sudden it's like 17,534 for some reason of something. I'm not even sure what this is. This is apparently a shape 512, 408, 408, 256, 512 shape. 408. Why are the numbers so regular? 336, 336. Okay. First batch. And then we just collate. We go through the indices of this one, which has, I think, 512 numbers. So we go through that and we just do shape of that is 512. So we start iterating through that one. And then we pick the data set, and the data set is going to be what exactly? That's the, okay, that's the our collated data set. So let's see how it's going to work. Let's enter here. Get the item. We are in the sampled multi. That makes sense. We have an index that we fetched from that frozen. And we say get dataset and index. Okay, let's enter. Bisect. This basically tells us where to go. Zero, one, it picks one, and then current indices of one. And then, so we grab that data set with that index to get that particular sentence together with its index. Let's enter here. So we are now in the language pair. Okay. And if we go even further, because this is a prepend dataset, we enter here. We're now in the prepend. And because prepend contains, underlying it contains mmap, we should now be in the mmap. Okay, exactly. So for this index, We grab its size and the pointer. Fair. And then we fetch the data. We convert it into NumPy. And here is our sentence. Okay, this is a very fuzzy sentence. Wait, this looks like an empty sentence. Or just a single token sentence. Interesting. So here we are, and now we append the token. And now we go up. So now we are again in the language pair. We do the same thing for source. We grab the data from the mmap. Again, very suspicious here. And then we append, and we are up there. Okay, and then should we append any of these? We don't. We just retrieve this. And that's the example. And that's the sampled multi. And then this just keeps on happening until we hit the collate function. So again, this happens until we hit the collate, which was here, epoch batch, which happened here from the dataset collator, which means, so what's our dataset? Our dataset was get batch iterator. Train. Just a second, where is the load checkpoint? We were here. And we were like, get the train iterator. Trainer. Here it is. Dataset. It's our multi. Let's find the multi-sample. Sampled multi dataset. Was it this one, the epoch one, or the regular one? Let's see here in the notes. Sampled multi dataset. And so here we're trying to find its collator function. Collator function is here. Okay, so let's just hit here. We are now here. Are we a shared or not? If you're shared, then we pick its underlying data set and its collator, and we grab the samples, out of which there's 512 samples. Okay, all of these are weird because they only have one token. That's maybe why it's dummy or frozen or whatnot. Okay, so we go through the samples, get the dictionaries. So we get a ton of dictionaries, and we somehow have to combine those dictionaries that currently just have ID, source, and target. Let's go inside here. So to get there, we need the language pair dataset, language pair dataset, language pair dataset. I think it's this one. Good thing I was writing down all of this, language pair dataset, exactly. So now we find its collator. That collator, is this inside of the language pair? It is. We expand it, and then we call this. So let's go here. So now we have a ton of samples which are dictionaries. And then merge a list of samples to form a mini batch. Samples to collate. Pad to length none. So what we do, we grab the samples. We grab the padding from the source. EOS. Left pad source true. Target false. Input feeding true should be. Pad to multiple 1. Let's enter the collate. Here's the collate function. We go through the samples, we grab the IDs, and then we call merge. Pad to length is none, so we return none here and true here. And then we call the merge, which is above. Let's see what we do here. Okay, collate the tokens. So we pass in the samples from the outer scope. Okay. And now we go through the samples. We grab the, if we grab them by the key, which is source, because we passed in the source. So what we do, we go through those and we grab the source tensors. And we grab the source tensors and we said, here's the padding token, here's the end of sentence token, here's the left pad true, move EOS to beginning false, pad to length, pad. Okay, so let's go and collate all of these by entering here. Let's see what exactly happens. Run F5. Just a second, guys. Let me just see something. Okay, guys. Doing some launch agreements. Okay, let's see here. So values. So we grab the values. The values are just source tokens. Okay. We grab the source tokens. And now we go through those. We grab its size of 0. It should be 3 because it looks like it's dummy. Yes. So it's 3 is the max size. And then we go, if pad to length is none, which it is, then we set size. And then pad to multiple. If this is true, then, which is not. So then we do what? Pad to batch size. Batch size is 512. If this is none, which it is, we grab the length of values, which is batch size is this. So now we say values, which is our set of tensors, list of tensors. We grab the 0th one. Aha. So values of 0. What will values of 0 give us back? Is it just the first tensor or what? Values of 0 is just the first tensor. And we say new batch size filled with padding tokens. Why would we do that? Why not just, okay, because it probably just keeps, what does the new do? I guess it just keeps the data type and stuff. PyTorch tensor new. Tensor new method, let's see what this one does. Constructs a new tensor of the same data type as the self. On the same, for CUDA, creates on the same device. What's the device of this one, by the way? Values of 0, device is CPU. All of this is on CPU yet. Okay, so we create this. And then we go and do what? We go through the values. Here's how we collate them. We go through the values and then we copy the tensor. So if left pad, which is true, we go here and we say result of I equals size minus the length of this one. So we copy the tensor into here. So that means copy the tensor from here to the very end, right? That means left pad, because we initialize it with the padding token. So that means here we basically go from size minus length of the vector and to the end. So we just pad it. And then the copy tensor is what? It's defined here. It's gonna grab the value and the destination, assert there's the same number of elements, and just copy from one to the other. That's it. So that's it. We ended up collating all of these. Return. That was the merge. And then we do what? We go through the samples. We again grab the source. If it's not equal to the padding, wait. But these are not the final results, right? So here what we do is, if it's not equal to the padding, convert to long and sum. If not equal to the padding, that means that's the content. So we grab the, okay, we get the actual lengths. Make sense? And then we sort the length in the descending order, and we preserve the sort order. Okay, so that's going to help us make sure we have similar lengths together, although all of these are going to be 3 in this particular dumb example. And then index select ID, we just permute them so that we have that order. And then we do the same thing here. We just permute them. That's it. Let's go. And then we're almost done here, I think. We merge the same thing. Target. This is going to be same as here. Although here we don't have padding, so that might be a bit different. And then path to length. If path to length is not none, otherwise none. So we pass same here. This path to length there was also none. Everything is the same except for the merge now doesn't have the left pad. So we end up with what? So this is now false. Left pad is false, so that means we end up with this being false. Left pad. Okay, so we end up, the only difference is here. Left pad, so we're gonna be doing this. So now we go and just reverse. We right pad. You right pad. And that's it. Exit. That was fairly reasonable to assume. So we have the target tokens, and then we again use the same sort order that we found for the source lengths, and then find the lengths here and sort them, and then find the lengths and sum them up. Number of tokens looks to be divisible by 3 because we always have dummy. We have 3, 617. How come? Shouldn't we have like 512 of these? We have 4 of these as opposed to source tokens. Because what's the target? So we have here language token. 2 is, I think, the end of sentence, and we have some 2 tokens here. Do we have a dictionary here somewhere so I can just decode and understand what these are? We are in the language pair dataset. I assume we have it somewhere, the dictionary. Okay. And then input feeding, we create a shifted version of targets for feeding the previous output tokens into the next decoder step. So shifted version of targets for feeding the previous output tokens into the next decoder step. Let's see, we again do the merge. And then we're almost done here, I think. Previous output tokens is, if it's not none, sample. It's very complex collating, at least on the first pass. And this has got to be the most legendary debugging session ever when it comes to data loading. This is fairseq data loading 101, at least for machine translation. Left pad, false. Move the end of sentence to beginning, true. This is different. And then pad to length. So this is going to be none. This is going to be left pad false, so we right pad. So the only difference is here move EOS. Let's understand how that's going to play out. So move EOS to beginning. So the difference will be here. We again have the values. What did we do? We grabbed the target. Okay, just a second. So we have the target being extracted from the samples. Shouldn't target be like 4? The values here are 3 only. I see size of 3, but we had 4 above. Just a second, let me see. Target here has 4. Because of what? Because we've done the merging. And maybe some of them were... I'm not sure what happened there. Merge. What's different between target and source here? Nothing. They're just left padding. And both are going to be none. So just the padding is the difference. And then if we go to here, well, let's see what's the size here. If it's 4, then that's explained. Okay. So apparently some of them have 4. Okay. Let's now go to here. So this is set to true. So in that case, what happens is, if EOS is none, which it's not, we go and we put to the destination, we put, okay, so the first one is going to be the EOS, and then the rest is going to be just everything else from source. Got it. So we just moved that as the last token to be the first one, as this flag here suggests. Move EOS to beginning. But why would we do that? Don't we have like EOS and then EOS? Why would you put EOS? Why not BOS? Beginning of the sentence. Put them to the beginning. Why would you put EOS there? I'm not sure, but let's exit here. Exit merge. Okay, so that's going to be the previous output tokens. And now, so we got our targets, and we just kind of shifted them. Okay. Length of samples, number of tokens, and this is the final, this is the dictionary we've been seeing all around the place. Target, source tokens, source lengths, all of that, but I don't see where is the previous token. We're gonna be, if it's not none, then we add this one as well, and we sort it as well. Okay, alignment, constraints, nothing, nothing, nothing. We return the batch. We're now back to the language pair data set, and we just retrieve it back, and now we're in the sampled collator. Because we were shared, we entered here, and we skipped the rest. And now we go back here, and that's it. And now reset just grabs that batch and sets the dummy batch. And we're done. We return back here, learning step, we don't care about that. We don't care about that. We have our epoch iterator. And then, so what is left to understand is also why did we have frozen batch being set before anything else? Let me see just quickly. Trainer.py. Oops, nope, not that one. Trainer.py. Why did we have reset dummy? Why was this set? Why was the batch iterator first batch already set? That's not clear as well. Okay, batch iterator first batch. How and where was this set? I couldn't catch it while debugging. Line K61 trainer.py. Okay. My battery might die, guys. If that happens, we're gonna continue after the lunch break. I'm gonna let you know in the Discord server. Let me just go back here. I think I might be at the very end of the battery life. Next, epoch IDX does what? Goes into this one. And if this is not none, we do what? End of epoch. Has next. So just return back this one. Where else do we call this one? We call it here. And then we call get train iterator again. With the next epoch index has shared sharded data. If it has sharded data, then we have to load again. And don't cache it. So load the data set. We did call that one here as well, right? When we were loading the checkpoint. Just a second, loaded the checkpoint. When we were grabbing the iterator, get train load set data set was set to true. So we're gonna go through the same process right now. We would go through the same process here. load dataset, disable, everything is the same here. So we just fetch everything again. mmap and then add the prepend dataset, prepend token dataset, and then above it, the everything we wrote down here. So above it would be this length per dataset, and then above it we'd have a sampled multi-data set. So I guess the difference would be is that we would sample a different set of indices, which effectively introduces shuffling. The only thing I'm kind of confused about here is you don't really have to repeat many of these steps. You'd only have to change the indices. It's kind of suboptimal, but I guess that's just a minor optimization. Okay, epoch iterator. Let's go to the train. Let's enter here. Let's see where it's used. Enter here, epoch iterator. We get the next epoch iterator. And then where is it used? In the validate and save, which we don't really care about. Just a second, train. Iterator. Okay. We'll continue, guys. We'll continue looping through, analyzing the program further to understand even better how this loading works, and then we're going to debug why I'm getting empty dictionaries. After that, I'm going to add some tasks to the GitHub project. That's the idea for the next stream. Could you give some advice? Somebody asks about what AI projects portfolio built to land in an AI company. For those types of questions, check out my blog on Medium and just join the Discord. There is plenty of people who can give you a lot of cool ideas for those types of projects. I already mentioned, like, it's really open-ended. You can do a ton of stuff. It doesn't really matter as long as you do something that's cool and creative. That's going to be a good project. So yeah, I know it's not probably a satisfactory answer, but it's how I think. Okay, guys, I'm wrapping up the stream, and the battery just died. So cheers.